So, today we are going to be looking at two applications of breadth first search, right. I am going to in particular look at applying breadth first search to finding out the connected components in a graph, and the second application will be to checking if a graph is bipartite. So, I will define what bipartite means and then we will see how to apply breadth first search for this. Okay. So, recall that a graph can be in many pieces. So, I could have a graph which looks like that. So, how many connected components does this graph have? 5, right. ये दो vertices भी connected components हैं. And what we want to do is have a procedure which will label these vertices. Okay. It will label every vertex here 1 to say that this is in the first connected component. I have just arbitrarily called this the first connected component, right. It will label every vertex here 2, it will label every vertex here 3, it will label this vertex 4 and it will label this vertex 5. So, that if, so I want a procedure which returns this labeling of the vertices. So, I will have an array called label, let us say, and for each vertex. So, this is the index corresponding to vertex v. At this location I should have 1, 2, 3, 4, 5, 6, 7, whatever is the number of connected components, that number should appear here. So, that by looking at this array, given any two vertices, I can just in constant time determine if they are in the same connected component or not, right. If they have the same label, then that means that they are in the same connected component. If they have different labels, they are in different connected components. Yeah. So, question is, how will I do such a thing? This is a very useful procedure. First, it is also counting the number of connected components your graph has. Yeah. How will I do this is the question that we are going to.
Do the BFS for each vertex, and if the vertexes and maintain one which counts the vertices which already have been traversed. So that way.
Right. So, okay. So, the standard thing, since in any case in the first slide I said it is an application of breadth first search, the first thing you are going to do is to do some breadth first search somewhere. कहीं से तो कुछ करेंगे, right. तो आपने मान लीजिए breadth first search के लिए याद रखिए that there is notion of a starting vertex, right, that we take one starting vertex and then we start doing our breadth first search from there. So, suppose I take this as my starting vertex and start doing the breadth first search. So, what is going to happen, right, I am going to give each vertex a, so there also I was giving each vertex a label, right, a distance, let us call that a distance label, and let us call this label component number, let us call this component number. Okay. So, now there what I am going to do is all the vertices that I visit. So, if I do a breadth first search from starting from this vertex, which all vertices am I going to visit? Only the vertices in this connected component. Is that clear to everyone? Right. In the very first step, in the first round, what I am going to do is I am going to look at all these 3 adjacent vertices and put them into the queue, right. So, these will get visited, then when I take this out of the queue, then I will put this into the queue and so on. So, I will end up putting all of these vertices into the queue, removing them, and so all of these vertices will get visited, but I would not visit any of these vertices. Yeah. So, I would only visit these vertices. So, as I am visiting these vertices, I can keep assigning them a component number equal to 1, right. So, I keep assigning whatever these vertices are, let us say these vertices are some A, B, C, D, E and F, and A appears here and B appears here and C appears here and D appears here and E appears here and F is here. I give each of these a label of a connected component number of a 1. Now, what should I do? So, initially what are the values that I give to each of these connected component numbers? Let us say initially everything is 0, right. So, now after I have finished this one BFS, some vertices have a connected component number of 1 and some others have connected component number of 0. Which are the ones which have 0? All of these. And which have a 1? These. Now what should I do next? Pick pick any vertex with z 0. Easier said than done. How do I pick any vertex with 0? Okay, so I just start from here and find the first vertex which is a 0, and then what do I do? And then so let's say this was the first vertex which was at a 0, very first. This is, let's say, this vertex here, so I start a BFS from here. ठीक है, एंड इसके अंदर सारे वर्टिसेस को अब क्या लेबल हो जाएगा, इसको हम 2 लेबल करेंगे, कनेक्टेड कॉम्पोनेंट नंबर इसको 2 देंगे, इसको भी 2 दे देंगे, इसको भी 2 दे देंगे. जब हम ब्रेथ फर्स्ट सर्च करेंगे तो इन सब के ऊपर कनेक्टेड कॉम्पोनेंट नंबर 2 हो जाएगा. तो ये जो सारी वर्टिसेस हैं, ये जहाँ जहाँ पे भी हैं उन जगहों पे 2 2 लिखा हो जाएगा. राइट, देयर माइट बी अ 2 हियर, दिस वुड गेट लेबल्ड 2, देयर माइट बी अ 2 हियर, this might also be 2, this might also be 2, something like that. Yeah. Now find the next 0. How do I find the next 0? Start from? Right. So this is where the small thought is required. I should not start again from the end. Start from where I found the last root vertex and continue from there, continue from the next location, right. And then once again when I find a 0, I start a breadth first search from there. Once again that will end up labeling certain vertices. Okay. Once again I start find the next 0 and so on and on. So this will at the end do what we wanted it to do. Question is, how much time does it take? Okay, how much time did this breadth first search take? Number of edges plus the number of vertices. Of course, number of edges is more than the number of vertices. Why? It's at least n minus 1, right? If a graph is connected, right, then there is a spanning tree in the graph. If there is a spanning tree, the spanning tree itself has n minus 1 edges in it. तो इसका मतलब connected graph में तो n minus 1 से ज़्यादा edges होंगी ही होंगी. तो इसमें हम नंबर ऑफ एजेस जितना हमने वर्क किया, ऑर्डर नंबर ऑफ एजेस, ठीक है. ऐसे ही इसके ऊपर जब ब्रेडथ फर्स्ट सर्च किया, इसके ऊपर भी उतना ही टाइम स्पेंड किया, ऑर्डर नंबर ऑफ एजेस. इसके ऊपर जब ब्रेडथ फर्स्ट सर्च किया उतना ही टाइम स्पेंड किया, ऑर्डर नंबर ऑफ एजेस. इसके ऊपर ऑर्डर नंबर ऑफ एजेस, इसके ऊपर ऑर्डर नंबर ऑफ एजेस. सो इज द टोटल रनिंग टाइम इक्वल टू ऑर्डर नंबर ऑफ एजेस? Is this the right number? Yes. देखिए, number of edges can be much smaller than the number of vertices in this entire graph. The graph could have 0 edges. Right. So we have not counted the time required for traversing this array to find the next vertex from which to start our breadth first search. And how much time does it take to traverse this array? Order n, exactly. Order n. Critically, because we are not going back from the starting when searching. Agar if we start always from the beginning, then it will be order n times the number of components. Yes. अगर हमने जो है शुरू से किया होता तब ऑर्डर n टाइम्स नंबर ऑफ कंपोनेंट्स लगते हैं, मगर हमने ऐसा नहीं किया. ठीक है, वी हैव जस्ट मेड वन स्कैन ऑफ दिस अरे, दैट्स क्रिटिकल. ठीक है, सो द टाइम रिक्वायर्ड फॉर दैट इज ऑर्डर n. सो द राइट टाइम बाउंड शुड बी ऑर्डर m plus n. Yes, you understand why I am saying m plus n here and not just m. It's not the case that m is more than n. It's not either the case that n is more than m. I can't say that because this is not a connected graph over which I am doing a breadth first search. Okay? So this would be the right thing to say. Or if you want to say maximum of m comma n, that is also okay, right? But just saying order m or order n is not correct. Okay? Yeah.
Like when you know A,
Yeah.
you start your breadth first from D. Then how do you label A without reversing? How do you label A as one without going through the array?
No. So I started my breadth first search from here, right? When I started my breadth first search from here, let's say you are saying you want to start your breadth first search from here, or Suppose I started my breadth first search from here. Then I looked at its adjacent vertices. These were B, E and F were its adjacent vertices. Yeah. These vertices I am going to put them into the queue. At the time I put them into the queue, I am also going to go to the location corresponding to these vertices in this array and mark them 1.
Sir, but without, sir, like you are saying, we go through the array only once.
Right.
Like
Yeah, we go through the array only once for selecting the root vertex, but for each one of these vertices, when I am visiting each of these vertices in my breadth first search, at that point I am going to go to that particular location in this array and label that vertex.
So, sir, you are not counting that time.
Okay, how much is that time? Constant for each of these vertices. So again, number of vertices is n, so again I would take order n time for that. Right, for each one of these vertices, okay, for each one of these vertices I am in any case spending a constant amount of time, because I am putting these vertex into the queue, I am removing them from the queue, right. I am actually going to give them a distance label also, although that distance label is not really required, but I am going to go access this vertex, I am going to spend a constant amount of time. So that in some sense I am kind of in that constant amount of time also accessing this array and updating that information here.
Sir, is the location where the next element, like A, from A you start, then where is B? Is it known directly? Where is B?
Okay, if I start from A, what is okay? When I start from A, how do I know what B, E and F are? So think of B, E and F as numbers, right? So when I look at the adjacency list representation of A, right, I have the adjacency list of A. I know what the 3 vertices adjacent to A are. They are, let us say, vertices numbered B is 2, 5 and 6. These are vertices numbered 2, 5 and 6. So I will go to locations 2, 5 and 6 in this array, right, and make them 1. Right. So you can just have a direct correspondence as numbers, if that is how you like to think of it. Yeah, clear to everyone? So we can determine connected components in so much time, order m plus n, linear time. Right. This is also called linear time. We have used this term before. I can remind you, such an algorithm is called a linear time algorithm. Great. So the next application we are going to look at is for what is called bipartite graphs. Okay, first let me define for you what a bipartite graph is. So we are given a graph G. So recall, a graph is given by a set of vertices and a set of edges. We are talking of undirected graphs here. G is a bipartite graph if there exists a partition of V into U comma W. Partition का क्या मतलब होता है? What does partition mean? V equals U union W, U intersection W equals null. Right? I can divide the set of vertices into 2 pieces, U and W, such that every edge has one end point in U and the other in W. हर एक एज का एक एंड U में होगा, दूसरा एंड W में होगा. Let me draw an example. ठीक है? This is an example of a bipartite graph. Every edge has one end in the set U and the other end in the set W, the other end point. That means that there is no edge like this or like this. these edges are not there. There are no edges both of whose endpoints are in U or both of whose endpoints are in W. ठीक है? Such graphs actually model a lot of things. One standard setting is these are boys, these are girls, and these reflect their whether they like each other or not. Huh? No, we are not saying they are getting married this way. We are just trying to find out if they can get married, right? Or these could be jobs and these could be applicants to jobs. Yes? And a certain applicant is suitable for a certain subset of jobs, and you want to know whether for each job there is an applicant or for every applicant there is a job, some such thing, right. So, such graphs find a lot of applications in these kind of settings. Question: given a graph, can you determine if it is bipartite? Right, everyone understands what the question is? Given G is G bipartite, so how will, so suppose you said the answer is yes, yes G is bipartite, how will you convince me it is bipartite?
The same level, because alternate levels will act as a particular partition.
Okay, so he has a suggestion. What he says is do a breadth first search. After all, that's the topic of this class, right? Do a breadth first search. From which vertex? Any vertex. Okay, let's do a breadth first search. So, I have said starting from an arbitrary vertex, just to make sure, just so that you understand that there is nothing sacrosanct about the starting vertex. कहीं से भी आप शुरू कर सकते हैं, ठीक है? आपने vertex V से breadth first search शुरू किया, तो आपका, if you recall, breadth first search will divide the graph up into layers, into levels, right? These will be the vertices at level 1, level 2, level 3, let's say level 4, and there were 5 levels. There was one other interesting thing that we had talked about as regards breadth first search. All the edges go, all the edges of the graph. We are not talking of the breadth first search tree. We are talking of the original graph. In the original graph, there will be edges which go between adjacent levels or within a level. There will be edges of this kind which go between adjacent levels. Yeah. And there might be some edges which go within a level. There would be no edges which jump levels. There cannot be an edge which goes like that. ठीक है? Color different है, dotted है और cross भी लगा दिया मैंने. So you should not confuse it with anything else. Right, everyone follows this. Okay, so these brown edges are not there. We have only the green and the red edges. When is this graph bipartite? Suppose these red edges were not there. Is this graph bipartite? Suppose there were no red edges. Which are the red edges? These are the red edges here. So, what do I mean by no red edges? There are no edges. Suppose all edges go between adjacent levels. हर एक एज बगल के लेवलों में जाती है, i.e. no edge has both endpoints in the same level. Suppose such was the case. What can you say? Right? This implies the graph is bipartite. Does everyone see why? Sorry, this, yeah, good. So, I am assuming, let us assume that it is a connected graph to simplify matters. So, given G is G bipartite, so let us assume G is connected. ठीक है, हम ये assume करते हैं कि हमारा पूरा ग्राफ कनेक्टेड है. अगर ग्राफ बहुत सारे कनेक्टेड कंपोनेंट्स में है तो we will have to check it for each connected component. If each connected component is bipartite, then the graph is bipartite. If some one connected component is non-bipartite, then the graph is not bipartite. I'll come to all of this in a second. Okay, so we, for now let's just assume that we are given a connected graph and we have to determine if it is bipartite or not. तो हमने ये काम किया, एक वर्टेक्स से शुरू हुए और जो है हमने एक ब्रेडथ फर्स्ट सर्च कर दिया. मान लीजिए ऐसा होता है कि कोई भी इस तरह की रेड एजेस नहीं आती हैं, एजेस विच गो विद इन द लेवल. द क्लेम इज दैट द ग्राफ इज बाइपार्टाइट नाउ. व्हाई? बिकॉज नाउ यू आर गोइंग टू टेक ऑल्टरनेट लेवल्स ऑन द यू साइड. सो ये आपका यू साइड पे हो जाएगा, ये भी यू साइड पे होगा, ये भी यू साइड पे होगा और डब्ल्यू साइड पे बाकी के हो जाएंगे. ठीक है. सो दिस इज द बाइपार्टीशन. After all, to show you that, to convince you that the graph is bipartite, what do I have to do? I have to show you a partition of the vertices such that every edge is going between one side, is going, has its endpoints on the two sides of the partition. So now, if I do my partition in this manner, ये u side है, ये u side है, ये u side है, then every edge is going from a vertex on the u side to a vertex on the w side. Yes, if these red edges were not there, but if these red edges were there, then we can't say, because then such an edge is going between a vertex on the w side and another vertex on the w side. So, if this were the case, all edges go between adjacent levels, that is no edge has both endpoints in within the same level, then G is bipartite. But we have not solved the problem yet, right? Suppose there is an edge which goes, which has both its endpoints in the same level. What then? Suppose such an edge exists. Does that mean that the graph is not bipartite? So you have not solved the problem, right? अगर हमने breadth first search किया और इस तरह की कोई एक edge आ जाती है, तो क्या हम ये कह सकते हैं कि ग्राफ bipartite नहीं है? हाँ? कह सकते हैं कि नहीं कह सकते हैं? So after, so if in the BFS we find an edge both of whose endpoints are in the same level, right. So, if in the BFS we find an edge both of his endpoints are in the same level, then what? What can we say then? Well, life cannot be too hard, right. So, then what? Basically we have to say the graph is not bipartite. Then G is not bipartite, but why?
So suppose it is bipartite, then the vertex that we started with must exist in some of the partition. Suppose it is bipartite and you have partitioned it in U and V. Then the vertex you started, this BFS must be in some partition, let's say U. Then this would definitely contradict, because the next level must be in V, the next level must be in U. Ultimately it will contradict that it's bipartite.
Okay, proof is correct. I will give you a different proof though, because it will bring out another aspect, another property of bipartite graphs. Okay. So, suppose we had such an edge. So, we had an edge. So, मान लीजिए हमें इसी लेवल पर एक edge मिल गई, both of whose endpoints are in the same level. ठीक है. Now recall we had a notion of a breadth first search tree. ठीक है. What was the notion of a breadth first search tree? We said there is a tree and basically for each of these vertices there is a predecessor. For each vertex there is a predecessor except for the starting vertex, the root vertex. तो इस एज के लिए एक प्रीडेसेसर है, मान लीजिए वो ये था. इस एज के लिए भी एक और प्रीडेसेसर है, ये था मान लीजिए. ठीक है. इस एज के लिए प्रीडेसेसर है. हो सकता है इस एज, सॉरी इस एज नहीं, इस वर्टेक्स के लिए, इस वर्टेक्स का भी प्रीडेसेसर मान लीजिए यही था. हो सकता है. तो अब हमारे पास एक साइकिल बन गई. साइकिल बनेगी ही बनेगी, बनेगी हमेशा साइकिल, क्योंकि इवेंचुअली या तो पहले खत्म हो जाएगा नहीं तो रूट तक तो जाएगा ही जाएगा. एक साइकिल बनेगी हमेशा इस तरह से. इस साइकिल की लेंथ क्या होगी, ऑड या इवन? इज दिस ऑड? काउंट करके आपने बताया ऑड है ना, हमेशा ऑड होगी. क्यों? क्योंकि हर लेवल पर दो दो होंगी और एक आपकी ये होगी. So if such is the case, then G has an odd cycle. ठीक है. अगर हमको इस तरह की एक एज मिलती है, इसका मतलब ग्राफ में एक ऑड साइकिल है. अगर ग्राफ में ऑड साइकिल है तो ग्राफ बाइपार्टाइट नहीं हो सकता. Let's prove that fact now. If G has an odd cycle, then G cannot be bipartite. I have not proved this fact, I will just prove it. But if I prove it, then we are done, right? हमें एक ऑड साइकिल मिल गई, इसका मतलब ग्राफ बाइपार्टाइट नहीं है, खत्म. हमने ये वाला थ्योरम अप्लाई कर दिया. ऐसा क्यों है? ये भी बहुत सिंपल है. अगर ग्राफ में ऑड साइकिल है तो वो बाइपार्टाइट क्यों नहीं हो सकता ग्राफ? ये आपकी ऑड साइकिल है ग्राफ में, खूब बड़ी सी बना लेते हैं. ऑड हुई इवन हुई, 1 2 3 4 5 6 7 8 9 10 11 12 13. ठीक है, ये ऑड साइकिल है. So proof by contradiction. Suppose the graph is bipartite. So what will happen? Suppose this vertex either it's on the u side or it's on the w side. Suppose it's on the u side, then this vertex has to be on the w side. Yeah, then this has to be on the u side. This has to be w, u, w, u, w, u, w, u, w, u. u and u के बीच में एक एज हो गई, कॉन्ट्रडिक्शन. ठीक है. सो ऑड साइकिल अगर ग्राफ में है तो ग्राफ बाइपार्टाइट नहीं हो सकता. I started with a u, but this could easily have been a w, and you would have two adjacent vertices which are both labeled w. Everyone follows this proof, right? So let me show the previous slide once again. If the graph has an odd cycle, then it cannot be bipartite. And if we found an edge both of whose endpoints are in the same level, then we have shown it has an odd cycle. This is the odd cycle in the graph, right? This is a general proof. This is not a proof by example, because ये predecessor at some point तो common होंगे ही होंगे. अगर यहाँ नहीं हो रहे हैं तो eventually यहाँ होंगे. तो ये जो cycle बनी अब आपकी, इसकी length odd होगी. Everyone follows this? ठीक है. So in this manner you can use breadth first search to check if the graph is bipartite or not. Yeah, which is equivalent to checking if the graph has an odd cycle or not. So if the graph has an odd cycle, then it cannot be bipartite. If the graph has no odd cycle, then does it mean it's bipartite? If all cycles in the graph are even in length, if all cycles in the graph are even in length, then does that mean that the graph is bipartite? Huh? इसका मतलब आपके समझ में नहीं आया. हाँ. So my next question is, if all cycles in a graph are even, is in a graph G are even, is G bipartite? Yes or no?
Because now the canonical graph arranged in the same level. So again the BFS tree will help.
Right. So once again, take your graph, do a breadth first search on the graph. ठीक है.
And if there is a common edge.
अब अगर कोई एक एज आती है विच इज बिटवीन द सेम लेवल, देन देयर इज अ नॉट साइकिल. तो कोई उस तरह की एज आएगी ही नहीं, क्योंकि इसमें तो सब साइकिल्स इवन है. अगर उस तरह की कोई एज नहीं आएगी तो आपने शो कर दिया कि वो बाइपार्टाइट है बाय टेकिंग ऑल्टरनेट लेवल्स ऑन वन साइड. यू हैव शोन इट टू बी बाइपार्टाइट. यस. How much time did our procedure take? The procedure to check if a graph is bipartite. How much time did it take? हमने क्या किया? एक वर्टेक्स से BFS किया बस. हाँ? And then what did we do? We did also something else, right? We checked if there was an edge, both of whose endpoints were in the same level. हाँ?
BFS another time we got it. When we make a BFS tree, then also we check same level.
उसी में ही हम चेक कर सकते हैं, राइट? क्यों? क्योंकि लेट मी राइट, जब हम ब्रेडथ फर्स्ट सर्च कर रहे होते हैं, सो वी लुक एट ऑल द एडजेसेंट वर्टिसेस, देन व्हेन आई कम टू दिस वर्टेक्स, राइट, व्हाट आर द वेरियस थिंग्स वी आर डूइंग व्हेन वी लुक्ड एट, सो वी लुक्ड एट ऑल ऑफ दीज and we put them into the cube and we gave them a certain color. What was the color we gave them? Gray. Right? So each of these vertices were colored gray. Right? Then I removed one of these vertices from the cube. Let's say I removed this vertex from the cube and I looked at its neighbors. Yeah? If any of the neighbors is gray, then we can stop the procedure. हाँ? केवल ग्रे पे should we stop the procedure? If a neighbor is white, gray or black? ब्लैक पे स्टॉप करना चाहिए प्रोसीजर कि नहीं स्टॉप करना चाहिए? नहीं, बट ऐसे भी हो सकता है. देखिए, इसका कलर तो हमने ब्लैक कर दिया, ठीक है, और अब यहां से यहां एक एज है, तो फिर तो हमें ये मिलेगी नहीं, क्योंकि जब हम इस वर्टेक्स को देख रहे होंगे तो ये तो इसकी अदर एंड पॉइंट ब्लैक है और हम कहेंगे कि ब्लैक पे तुम नहीं स्टॉप कर रहे. हाँ, पहले जब हम इस वर्टेक्स को हमने देखा होगा तब हम इसको चेक कर चुके होंगे कि इसका दूसरा एंड पॉइंट ग्रे है कि नहीं. फाइन पॉइंट है, सबके समझ में आया? नहीं. आई विल रिपीट. ऑल यू नीड टू डू इज टू चेक if the other end point of the vertex is gray or not. Just gray. If it is gray, stop, exit, reboot. The graph is bipartite. ठीक है? Graph is bipartite. Is not bipartite. Sorry. Okay? And that's the only thing we need to check. Why is that? The reason for that is that, देखिए, we don't need to. If the other end point is black, then that does not mean that the graph is not bipartite, because you could have such an edge. Right, when I am looking at, so let me draw this picture again because this is getting cluttered. Right, when I am looking at this vertex, yeah, then it has its neighbors, one of which is this, which is already colored black. Right, so I cannot use black, the other endpoint being black, as a test for non-bipartiteness, because this could very well be a complete, this could be the entire graph for all I care. Yeah, this is clearly bipartite. Yeah, but to say that this vertex, when I am looking at this vertex, it has a neighbor which is black, you know, and use that to say it is non-bipartite would be wrong. Now, what we are saying is that suppose there is an edge like this. Yes. Now, when there is an edge like this, then when I am considering one of its endpoints for the first time, right. Then the other endpoint, since it has not been considered yet, would be colored gray. Yes, since it would be colored gray, we will be able to identify that edge as an edge which is running within the same level. Right. BFS may
So, but the children of the children of that leftmost node will also get in the queue.
they will also get into the queue, yeah.
And sir, if we then
जो पिछले वाले में उनको सारे मिले थे
the children of the other of some other nodes, sir, and suppose one of the children is found, sir, that will be gray only. So
Right, great. Here's a valid point. I made a mistake. Does everyone understand his question? No. चलिए. So okay, let's look at this picture for now. Right? अब मुझे आप बताइए कि इस पॉइंट पर किन वर्टिसेस का क्या कलर है इस पॉइंट पर व्हाट इज द पॉइंट डिपेंड्स अपॉन मी वेयर द पॉइंट इज आई हैव दिस इज द थिंग दैट हैज बीन सो दिस शुड बी ब्लैक क्लियरली right this should be black because it has been expanded out right and then since it has been expanded out all of these guys are in the queue they are all gray what are the color of these guys because they have not touched I have not touched them yet they are in the queue they are gray yeah now who can tell me what I am trying to do
say even this you would
if now suppose I look at this vertex next
be saying कि
and this has an edge going here right now the other endpoint of this edge is gray so I might say it's not bipartite but that's not right so simply level check कर लीजिए ठीक है अदर एंड पॉइंट का देखिए कि लेवल सेम है कि नहीं ज़्यादा दिमाग मत लगाइए ग्रे व्रे के चक्कर में ही नहीं पड़ेगा ठीक है वी आर कीपिंग लेवल नंबर्स so that's why that quantity is important that level number business is important we are keeping the level numbers of the other vertices so if the level number is the same say the graph is non bipartite if the level number is different continue yeah clear great okay Okay, so one thing I wanted to do today, which I think I did not do very well in the last class, was to argue that the level number of a vertex, that your breadth first search procedure is giving you the shortest path, right. Some of you perhaps understood it, but I think I did not do it very well. So, let us do it once since we have some time today. So, let me write down the formal statement. What I want to argue is that so in a breadth first search, starting from vertex V, the level number of vertex U is the length of the shortest path from V to U, right. What are we saying? We are saying that well I started a breadth first search from vertex V, I got a bunch of levels, right. Let us say vertex U is sitting in this level 4, 11, 2, 3, 4, right. Then the shortest path. So, what do we mean by shortest path? Let us define what shortest path means first, right. So, you all understand what a path is. So, between V and U there could be many paths in the graph, right? There could be many paths in the graph. It could be some very complicated graph. Each of these paths has a certain length. What is the length of the path? It's just the number of edges on the path, let us say. For now, we will just keep that as the definition. Later, we will modify this definition. So, for instance, if I were to look at this path, this has 1, 2, 3, 4, 5, 6 edges on it. So, it has a length of 6, right. If I had gone like this, it was even longer, it had length 7. If I had gone like this, 1, 2, 3, 4, 5, this had length 5, but there is also a path of length 4, this is 1, 2, 3, 4. Yeah, it is not important here exactly which it is, but you understand that there could be many different paths in a graph between two vertices, right, and the shortest path is just the path which has the least number of edges on it. Yeah, it is relevant clearly because if these are certain roads or some such thing, you would like to travel the minimum possible. Although I have not kept any distances here, but let us say these just reflect the number of hops that you are taking. Say suppose this is some computer network, you want to talk between V and U, right, and let us say most of the time is spent in when you have to go through one node, right. This is a link between this computer and this computer, this is a link between this and this, this is a link between this and this. So, information travels very fast on a link, but at a node, at a computer, it has to be processed and forwarded and stuff like that. So, there is a lot of time wastage there. So, clearly you would like to minimize, this is called the number of hops then, right. So, this path has 6 hops on it. So, you would like to pick a path which has the smallest number of hops, because then your information travels very quickly, right. So, you would like to find the shortest path. So, the claim is that if this vertex u is at level 4, then the shortest path from V to u is of length 4. So, first let us show that there is a path of length 4. How do I show there is a path of length 4? Very simple. I start from u, I take its predecessor, yeah, its predecessor would be some vertex there. Then I take its predecessor would be some vertex at the previous level. You understand what predecessor means? Let me recall, predecessor is the vertex which gave, due to which this guy got its label, and clearly that is a vertex sitting here, the predecessor of this, and I would get to the predecessor of this, and clearly the predecessor of all of these vertices at the first level is the root vertex itself. So, what is the length of this path? It is just the number of levels, and it is 4. So, there is a path of length 4. Can there be a path of length 3? If there is a path of length 3, then we will have to jump a level, which violates the fact that this is a breadth first search, right. This is a partition induced by breadth first search. Okay, you understand? If there is a path of length 3, then that path cannot visit all these. It has to come here, it has to start from here, but then it cannot visit all these 3 levels. So, it has to jump one of these at least. But if it jumps a level, then it's a path, then it violates our breadth first search property, right. That shows that this process gives you also the shortest path, right, and the shortest path is just the distance, the level number of each vertex. So, if I wanted to find the shortest path from a certain vertex, all I have to do is do a breadth first search, and the level number would give me the length of the shortest path. Okay, great. Now, one last thing I want to do with you is again applications of breadth first search. So, very simple application using this fact that we just understood. I give you a graph and I define the diameter of a graph. Okay. What do you think the diameter of a graph should be?
Maximum level in the BFS.
Huh?
Maximum level in the BFS.
Maximum length of
From the point of
maximum distance between two vertices along the shortest path between those two vertices.
along the BFS level.
The maximum level.
Maximum distance between two vertices in G. Let's just say that, where what does distance between two vertices means? Distance between two vertices equals length of shortest path.
Length of the shortest path. Now how do you define length?
Right? We are not saying that the diameter is the length of the longest path between two vertices. That is a very hard quantity to compute. That is impossible to compute, more or less. Okay? Right? So, we are not talking of that. So, diameter is very specifically defined, the maximum distance between two vertices, and the distance between two vertices is the length of the shortest path. How am I going to find the diameter of a graph? हाँ? किसने बताया मुझे क्या? What is the answer? BFS. Just do a BFS. Huh? Just do a BFS, and let's say the largest level number is 3. So the diameter of this graph is 3. That's not true. That's, yeah. We'll have to do a BFS on every node.
And then find the maximum.
And then find the maximum level number. You know, you understand why this is wrong? Does everyone understand why this is wrong? Because I could have a graph which looks exactly like this. Suppose this is my graph, right? So it's exactly this. If I did a BFS from here, I would get exactly level 3. But the diameter of this graph is not 3. The diameter of this graph is 6.
Like this.
Yeah?
On the leftmost.
The diameter is 6, right? Because it's the maximum that we are interested in, right? So to get the diameter, I would be able to get to the diameter if I started my BFS either from this vertex, or from this vertex, or from this vertex, or from this. If I started from one of these, then the maximum level number would have given me the right information. But I do not know which these vertices are, so I will have to try it out for every vertex, right? So how much time would determining the diameter take? Mn time. Right? We are assuming the graph is connected, right? So for so it will take, why? Because each of these breadth first search will take m time, and we are doing n.
So diameter is not defined for a disconnected graph.
For a disconnected graph, it's not defined. Let's just say it's infinite.
Only for components.
For each connected component, you can define the notion of a diameter, right? But if I do a depth first search from one vertex and I look at the largest level number, it doesn't tell me what the diameter is exactly, but it does tell me approximately what the diameter is. It can be at most half the diameter. The maximum level number is at least half the diameter. Yes? The diameter cannot be more than 2 times the maximum level number
For any BFS.
for any BFS. You understand? So diameter of the graph is going to be less than or equal to 2 times the maximum level number in any breadth first search. You understand why? Right? क्योंकि आपने यहाँ से एक BFS किया, आपके कुछ लेवल नंबर्स आए, ठीक है, इतने लेवल आए, मान लीजिए 1 2 3 4 5. The claim is diameter cannot be more than 10. No two vertices are more than 10 units apart. Why? Take any two vertices. आपने मान लीजिए एक वर्टेक्स यहाँ लिया, एक वर्टेक्स यहाँ लिया, इसका डिस्टेंस यहाँ से 3 है, इसका डिस्टेंस यहाँ से 5 है, ठीक है, तो आपको एक पाथ तो मिल गया जिसकी लेंथ 8 है, तो शॉर्टेस्ट पाथ की तो लेंथ 8 से कम ही होगी इन दोनों वर्टिसेस के बीच में, ठीक है. ऐसी अगर आपने यहाँ लिया होता है, यहाँ लिया होता है, तो इन दोनों वर्टिसेस के बीच में एक पाथ है आपके पास जिसकी लेंथ 10 से कम है, 10 या 10 से कम है। ठीक है, क्यों? क्योंकि हम प्रीडेसेसर लेंगे, इसका, इसका प्रीडेसेसर लेंगे, इसका प्रीडेसेसर लेंगे, इसका लेंगे, इसका लेंगे, हो सकता है ये यहीं पे मिल जाए, तो 10 से कम हो गई। अगर यहाँ पे भी नहीं मिलते तो यहाँ तो मिलेंगे ही मिलेंगे, तो 10 हो गई। तो इसका मतलब शॉर्टेस्ट पाथ की लेंथ 10 से कम होगी। तो इसका मतलब डायमीटर, since for this is true for every pair of vertices, the diameter cannot be less than 10, cannot be more than 10. So diameter is less than 2 times the maximum level number, and diameter is greater than, what is the diameter greater than? Maximum level number. So diameter we know is at least 5. Why? Because there is this vertex here and one vertex here, जिनके बीच का distance जो है 5 है. So by doing one BFS, you can get an approximation to the diameter. आपका एक BFS किया, उसमें level number maximum 6 आया, तो you know diameter is at least 6 and at most 12. अगर इतने से आपका काम चल जाता है तो अच्छा है, नहीं तो आपको फिर mn टाइम स्पेंड करके exactly diameter कंप्यूट करना पड़ेगा. Clear to everyone? ठीक है. So with that we'll end today's discussion on breadth first search. Tomorrow's class, in the next class we are going to look at depth first search.